Okay, welcome back. In this problem, we're going to be investigating a situation that's going to involve the use of Bernoulli's principle and what's known as a continuity equation. Take a look at the problem statement, and it's pretty long and complicated, so make sure you understand what it's saying, what information is provided, and what it's looking for before moving on. So in this problem, we have a house, and we're imagining that a bunch of rain is falling on the roof vertically. And all that rain is being collected by these gutters, which are going into what's called these downspouts. And then those downspouts are feeding into this pipe horizontally, this pipe called M, which goes into the sewer system of some sort. And at the same time, as this water is flowing that way, there's some water caught in this drainage pipe. And at a certain point, as this water is going here very quickly, it may cause the water in this drainage pipe to overflow. And the question is, how much rain, how fast does the rain need to be falling on the roof for the floor drain to overflow? What we're going to do here is imagine this entire system as a series of pipes, or maybe one long pipe. But the pipe's cross-sectional area is changing. And as the area changes, the speed at which the water flowing through it changes, and as the height changes, the speed can change as well. So again, kind of think about it this way. Think about the roof as part of that pipe. And essentially, the pipe is, the roof is very, very wide, so it's a big mouth pipe. And that's all feeding into this very skinny pipe, which is the downspouts. And that further feeds into pipe M, etc. What we're going to do is relate the rainfall in that wide mouth part, which is essentially the roof. We're going to relate the rate there to the rates and the heights and stuff everywhere else. So that rate at the top, I'm going to call that roof part 1. So in Bernoulli's law, you want to identify a few key places, and then use Bernoulli's principle to relate the velocities, pressures, and heights at those places to one another. Point 1, I'm going to label in this diagram as basically the roof. And so the velocity of the water coming down in the roof is going to be V1, and the area, the cross-sectional area will be A1, etc. And then the point 3, I'm going to label as in pipe M. It's in pipe M, but it's right beneath this drainage pipe, okay? And I'll make this distinction of why I did this a little in a moment, but this is a very kind of subtle problem in this sense. So the water is coming this way, and point 3 is saying what is the velocity in the water. At point 3, it's moving that way. What's a cross-sectional area? What's the pressure, etc. Right above it is a drainage pipe. So right above point 3 is point 4, but the distinction is that point 4 is actually in the drainage pipe. And then point 2 is the top of the drainage pipe. All right? So what we're going to do is relate a couple of these points together, and we can use Bernoulli's principle to find maybe the velocity here as a function of other quantities over there. Let me write down Bernoulli's principle real quick. It's 1/2 rho v squared plus rho gh plus a pressure equals constant. So what this means is that this quantity at point 1 is going to equal the same quantity at point 3, etc. And so we're going to kind of use this at different points to find out various quantities. So on your own, why don't you go ahead and relate these values at point 1 to point 3. And you can also use another equation, which is the continuity equation. And that says that the product of the velocity and the cross-sectional area at a particular point will always be the same. So the product of velocity and area at 1 will equal the product of velocity and area at 3. And this can be used to get rid of some of the quantities in Bernoulli's law by substituting velocities and areas. On your own, go ahead and try to use Bernoulli's principle to relate points 1 and 3. And there's going to be a bunch of unknown quantities, which we'll deal with in a moment. But for now, use this at points 1 and 3, and then also use this to maybe get rid of some of the quantities that we are not interested in. All right, so equating Bernoulli's principle at points 1 and 3, we find 1/2 rho v1 squared plus rho g h1 plus p1 equals the same thing at point 3. In this case, the height of point 3 is basically 0, so I'm going to leave that term out. And then we can also use the continuity equation to get rid of velocity 3. Remember, we're looking for v1. Let me write that down here. Because we want to know the rainfall rate in this part of the system, which is the velocity in the roof, which is v1. So I'm going to leave v1 in, but I'm going to use this to get rid of v3. So use the continuity equation, which says v1 a1 equals v3 a3. All right. And I'll just plug this in. I'll solve this for v3 and plug it in there. And then once we do that, we find 1/2 rho v1 squared. So as this plugs in here, I'm going to get a fraction squared. I'm going to move it over here. So I'm doing this all in one step, but you can just check it on your own if you'd like. A 3 over A1 squared plus rho GH1, and then these P1s and P3s I'm going to put on the right side. All right, so what do we know? We know the cross-sectional area of M, which is A3. I didn't write that up there, but we know that it's given in the problem statement. We know A1. Now A1's a little subtle. A1 is, again, think of the roof as a pipe. A1 is its cross-sectional area. So it doesn't matter how steep the roof is, all the water is still gathering inside the roof. And the cross-sectional area of that is going to be basically the width times the length. And the length is given in the problem as well. You can think about it this way. If the roof wasn't steep, but it was kind of maybe a little shallower like this, not as steep, it would still have a cross-sectional area, but now the cross-sectional area pretty much looks like a rectangle. Same cross-sectional area, even though it's not steep. So in this case, the cross-sectional area A1 is W times L. So we know these areas. Velocity 1 we're looking for. We know H1. We don't know these pressures, though. And this is why I kind of wrote it like this, because in this situation, you can see what's happening here is that this water coming down on this roof is coming down very quickly and essentially creating a pressure. Well, the water is flowing here very quickly. So it's coming here actually relatively slowly. And because this area is much smaller, it's going to flow much faster here. That's going to create a pressure that pushes upward at point 3. But now if I look at point 4, they're right next to one another. So the pressure at point 3 pushing up is going to equal the pressure of point 4 pushing down, because we want the water in this pipe to be stationary, about to overflow but not moving. So basically that's telling us that the pressure at point 3 and point 4 are the same, even though the velocities are different. The velocity of the water in pipe M is flowing to the right very quickly. The velocity of the water in this drainage pipe is not moving at all. So their pressures are equal. And so what we're going to do now is use Bernoulli's equation between point 2 and 4 to relate what we're looking for at to relate maybe some quantities we may know at point 2 to a quantities at point 4. And since these pressures are equal, maybe we can get rid of something. So maybe this will become a little clearer with the math. So on your own, again, do the same thing. Apply Bernoulli's principle between points 2 and 4. Write down an equation and see if you can maybe get rid of some other quantities here. And we'll come back and take a look. OK, so comparing points 2 and 4 and using Bernoulli's equation once again, we find, I'll write it over here, we find 1/2, well, we don't need that term, right? Because at 2 and 4, the water is stationary, so there's not going to be any velocity terms. So all we're going to have is rho GH2 plus P2. That's at point 2. And then the same thing for point 4. But point 4 is basically, again, at the bottom here, where the height is 0. So that's just going to equal the pressure at point 4. And so we get rho GH2 equals P4 minus P2. And as I noted a moment ago, P4 and P3, they're adjacent. So the pressures are going to be equal because everything here is in equilibrium. And so that's just going to be P3 minus P4. Now, sorry, P3 minus P2. Minus P2. So what this means is that, well, we have an equation that's very similar between this and this. We have a P3 minus P1 here and a P3 minus P2 down here. And actually what's nice is that if you look at points 1 and 2, they're open to air, so they have pressures of equal to atmosphere. So we can actually write this just equals P naught, where P naught is atmosphere, and this equals P naught, where P naught is atmosphere. So this quantity equals that quantity. So we can go ahead and plug in rho GH2 for this part of the equation. And so then we get this side equals rho GH2, all the rho's cancel, and you can solve for V1. And what you end up with is V1 is the square root of 2G H2 minus H1 divided by this quantity right here. And there's an approximation that I've talked about in the written solution to this, which I'm not going to get into here. But what's important is that we have all these quantities. And again, to reiterate, A1 is the cross-sectional area of the roof, because the roof we're considering as a pipe. Water's flowing vertically, so the cross-sectional area must be its area, which is given by W times L as it's coming out. So that square, or that rectangle rather. And then A1, the area of A1 is going to be the diameter of this pipe M. And the radius is given in the problem statement. So you can get all those numbers. Plugging everything in, and again, this is discussed in detail in the written solution, you get 7.84 centimeters per hour. Now, let me just point out a few things about this problem. So the way the problem is kind of set up, it looks a little almost counterintuitive in the sense that I have a bunch of different points here that I'm relating, and I kind of had to think about that, how to use which points here. But if you see some written solutions of this, a lot of them will just have points 1 and 2. Now, the reason I didn't do it that way, even though it ends up giving you the same answer, is that physically it's not very meaningful. And the reason I'm saying this is because, well, you want to find V at point 1, right? And yet, if you use a continuity equation at point 1 and point 2, then you would have V1A1 equals V2A2. But V2 is 0 because none of the water is moving at A2. So that would kind of imply to you that V1 must be 0. So it's a little weird if you try it that way. And then, so then the book solution gets around it by saying, well, let me use the area here. But the area here is not the same thing as the area in that pipe. So you really got to think about it point by point and be very specific about which part has what velocity. And when you have, in this situation, really we considered it as 2 different systems. One system was the roof plus a downspout plus M. All right, and so the water is flowing in that system in one direction. And so I considered that in the first part of the problem. And then we basically use that to relate some pressure in that system right here to the separate system of the drainage pipe. And that system we considered as a single system where water is not moving. And that's the second equation down here. All right, so I did consider this in 2 parts, and physically that makes more sense because Bernoulli's equation is really meant for situations in which a water flows continuously. If you considered it like this system, water is flowing out of that system, which we're not accounting for. So it's not physically meaningful. And that's why I solved it as such. There's more details given in the solution, in the written solution if you're interested, but let me stop here, and I'll end the video here and we'll cut to the summary. Thanks.